Hello, welcome to the video on phase 4, and the primary focus on phase 4 was to get the addressing modes done to a point where they're testable, and we can troubleshoot and test them with various instructions. Phase 4 is a bit of a code smash, because all I wanted to do was get everything, like I say, the addressing modes and some of the instructions and things tested. So to do that, obviously the addressing modes are in here, and I'm not going to go through these verbatim because we did a complete video on how the addressing modes work. There is one small note actually, in the fact that these addressing modes, although they work and they're functional, they're not quite right, and I changed them in version 5 because I start to use pointers rather than call by reference, because these work great. This way works great in phase 4 for anything that reads memory. It's not so good for writing to memory, so that's why the change gets made, but that'll get covered in the in the videos on phase 5. The main change to this routine here, the main function, was in the execute routine, and in the execute routine I use a global variable called done. And that's set to 0, and this while loop will continue up until the point where done is set to anything other than 0, and therefore it will just keep executing instructions. And the terminator for that execution is within the RTS instruction, the return from subroutine, and the RTS instruction just says if the stack pointer is not equal to FF, then actually perform a normal RTS. And the fact that you reload the PC, the CPU program counter, from the stack and change the stack pointers as we've discussed previously. But what it says is if the stack pointer is equal to FF, then therefore there's nothing to return from, because we didn't do a previous jump to subroutine. We didn't manipulate the stack, and there was no jump to subroutine, and therefore our presumption is that actually what we're doing is breaking out of the program and jumping back to the monitor. So I kind of like this routine. It's a lot cleaner than trying to implement a break function. I did have a look at doing that, but the way that the break function works is a bit weird. I might come back to that at some point, but anyway, that's how this works now. And as a part of that, I started to create more and more routines inside of the memory array initialization routine, and it allowed me to do much more. Let me just see if we can spot something there. So we could do this one, for example, and this was specifically to test the addressing mode, not necessarily to test the LDA instruction. In fact, the LDA instruction isn't quite right at this point. And if we have a look at it, I'll point out why it's not quite right. Where are we? So within the LDA instruction, so all the addressing modes are here. That's fantastic, but the problem it's got is it needs to actually manipulate the status register as part of the LDA, and that's not installed. That's not included in this particular code. So again, phase 4, although it says completed, the completed there means it's completed and tested as working with the addressing modes, not completed and tested as working as a function. And we can demonstrate that in action. So if we go back to our routine here, what we can see is that the LDA with the X index is saying load something from D000 plus whatever X is. Well, at the moment X is 0, so it's going to load it from D000, and if we go down and have a look, D000 has the value of DA. So post that instruction there, once that instruction is executed, then we would expect that DA will be loaded into the accumulator. So if we say go on C014 and then display the registers, and indeed we do see that DA is in the accumulator, and that the program counter has been incremented to the point after the RTS instruction, which is bang on, because the RTS instruction is only 1 byte, and therefore C018 would be the very next instruction. And if we were to run that from D0, which is saying load the accumulator with the value offset by y. Well, there isn't anything in y, and therefore you can say load it from D001. Well, D001 has dB in it, and therefore we could just say go, because the go instruction, as you remember, either goes from where your program counter points to, or where you specifically tell it. So we say go and then display the registers again, and the program counter is incremented as you would expect, and dB has indeed been taken in from D001, which is precisely what we wanted, which is all well and good. So I also wrote these for increment X and increment Y because they're very simple routines to write as well. So if you say go here on 0xC022, that will increment X, and if we display the registers again, we can see that X has been incremented. Now this wouldn't be a very good test because D000 plus X equals D001. Well, D001 has already got dB in it because we did the load Y. So what we can do is we can rerun that again, and we can say go on 0xC022, and that will increment the X register again. So this time, if we run the instruction at C014, which was the load X there with the load accumulator with the X index there, X is now 2, so it will be D000 plus 2. Go fetch this here, that should make the accumulator equal DC post that instruction. So if we now go back into here and say go on 0x014 and then display the registers, indeed that works. Now, as pointed out before, the LDA at the moment is not playing with the status registers because by rights the sign bit, the negative flag, should be set at this point, and the reason it should be set is because this value here, or well, in all of these cases it should have been set, they are greater than 7F, and 7F is the biggest value you can have before you flip bit 8. And bit 8 is the sign bits, and as we discussed previously, the CPU doesn't differentiate between a negative number and a positive number. That's down to the programmer to do, but this sign bit will always get flipped if bit 8 here is a 1. So that's pretty much the bottom line of what I did in phase 4. The other thing to note is that you can test. There's a lot of things in here that allows you to test 0 page and 0 page with X and 0 page, with Y and so on. But I mean, they can be tested. Phase 5 actually starts adding to a lot of these commands, in so much as we start to add the status register manipulation and other things. Plus, we change the way the addressing mode functions work. This really is just a brief overview of what I was aiming to achieve with phase 4 code. It was to get the bread and butter, the bones of the addressing modes working, testable, repeatably testable, and make sure that the emulator is actually returning the values you would expect it to return when you actually run those commands, plus a way to actually execute those commands to a valid stop location